Okay, so for this chapter, okay, what we are going to do is we are going to understand how to measure the flow rate. Okay, so flow rate, what is the symbol? Okay, the symbol for flow rate is actually V dot. Okay, so one of the fundamental formula that we can use is AC lah. Okay, V dot is equals to AC. This is the formula for flow rate. So what we hope to do here for this chapter is to measure this V dot. Okay, we want to measure, not calculate. We want to measure this. So how can we measure this? All right. Based on chapter 3, okay, we will need to use the chapter 3 knowledge for this chapter also. Chapter 3, we measured, what did we measure? We measure pressure. Okay, so for chapter 3, we actually measured pressure. Okay, so we can measure pressure by means of using a barometer, a manometer. Okay, so these are some of the ways. Also, a simple manometer is something like that. So we have a pipe, then we connect it to a open manometer. Okay, so fluid is flowing. Okay, so in this manometer, we can have the mercury or whatsoever. Okay, so it will go up to a certain height. Okay, so this height here, H, will represent the pressure head. So we can convert this pressure head into pressure by multiplying rho GH. Okay, so this is what we have done in chapter 3. We actually measured pressure. So for pressure measurement, what we call this is actually a direct measurement, because we can measure the pressure directly through observation. Okay, so in this case, we can determine the pressure based on observation of the height. Okay, on the other hand, for chapter 5, all right, it is not so easy. Okay, because for flow rate measurement, okay, the flow rate measurement, this one we have to go through a indirect measurement. Okay, indirect measurement. Okay, so as I mentioned, all right, so for the flow rate, we are going to go through indirect measurement. Okay, what do you mean by indirect measurement? Okay, because we cannot, there's no physical parameter that we can observe for the flow rate. All right, it's not like pressure. So pressure, we can actually observe the height. Okay, so but flow rate is more like knowing how many liters that is flowing through cross-section area per unit time. Okay, so it's not as simple as pressure. So how are you going to do that? This chapter will address this issue. Okay, so let's start. Okay, so the objectives of this chapter here, all right, is to be able to study flow measurement using a few measuring tools. Okay, we have Venturi meter, Orifice meter, and pitot-static tube. Okay, so since this is indirect measurement, so we need to do some kind of processing lah. Okay, we need to process the results in order to get the flow rate. So to be able to process the result, we are going to apply our Bernoulli's equation that we learned in chapter 4. All right, so we'll be using or we'll be studying these 3 measurement tools. Okay. Okay, so irregardless of which instrument we are using, okay, the principle for flow rate measurement is almost the same. Okay, so what is the general principle for flow rate measurement? Okay, the first thing is we need to create some form of a constriction or obstruction to flow. Okay, so this constriction or obstruction to flow will result in a pressure drop. Okay, and when there's this pressure drop, we can directly measure the pressure drop with a gauge. Okay, then with this pressure difference, okay, we can apply our Bernoulli equation to calculate velocity. And once we have the velocity, we can apply our equation to finally calculate my flow rate. Okay, so you see, we are not able to directly measure flow rate, but instead, okay, we use some form of obstruction to result in a pressure drop. Then we measure the pressure drop. So pressure is the only thing that we can directly measure for this case. Okay, so why does this principle work this way? So if let's say if you look at our continuity equation, A1 C1 is equals to A2 C2. Okay, so if we try to create a obstruction, means that we reduce my cross-sectional area. If I reduce my cross-sectional area, the flow speed must increase. Okay, so that is step number one. Next, based on our Bernoulli principle, P over rho G plus half C square over 2G. Okay, this must be a constant. So if this is a constant, so when we reduce the velocity, okay, the effect of this is the pressure will increase. Okay, can. So if the pressure increase, all right, okay, we will be able to measure this pressure. Okay, can. Same thing, if the velocity increase, the pressure will drop lah. So either way is okay. All right, there should be an inversely proportional relationship. If the velocity drop, pressure will increase. If the velocity increase, pressure will drop. So by measuring this pressure drop, okay, we can then use our Bernoulli equation to calculate my velocity. Then finally, use my V dot is equals to AC to calculate my flow rate. Okay, so this is the general principle of flow rate measurement. So the study examples will be these three: okay, Venturi, Orifice, and pitot-static tube. We will try to cover the first two here today lah. Can? Okay. So what is a Venturi meter? A Venturi meter looks something like this. Okay, as you see in the diagram here. So the constriction that we are talking about is this point number 2. All right, so you see that the cross-sectional area of this Venturi meter is purposely reduced. Okay, reduced. So the cross-sectional area is reduced and narrowed to 0.2. All right, so we will expect that when the cross-sectional area reduced, A reduced, okay, it means that the velocity will increase. Okay, so when the velocity increased, okay, the pressure will drop. Okay, as what we mentioned previously in the previous slide. Okay, so this pressure drop will result in a higher reading here. Can you see? Okay, so the pressure here is lower. Pressure here is lower. Okay, so the manometer reading here is higher. Whereas over here, the pressure here is higher. So the manometer reading is lower. Okay, so the delta P that we are talking about is the difference between these two. Something that we can observe, something that we can measure. All right, so this is the basic principle of a Venturi meter, okay, which follows the same principle that we discussed in the previous slide. Area drop, velocity increase, pressure drop. Okay, so this pressure drop will be reflected from this manometer. Okay, so how are we going to apply the equation to calculate the flow rate? So first step, okay, of course, is we apply our Bernoulli's equation. Okay, so for this case, we will assume that Z1 and Z2 is 0. What is Z? Z is the height. Okay, Z is the potential head. So today we assume that point 1 and point 2 is along the same height. Z1 is equals to Z2. Okay, and in this case we can set it as 0 lah. So Z1 and Z2 can be cancelled. So if Z1 and Z2 cancel, we can rearrange the equation to look like this. Okay, remember, what we want to calculate here is my C. Yeah? So therefore, we make C the subject. Okay, can. So maybe I will just open another slide to show you the derivation. Okay. Okay, so what we have just now was C2 square minus C1 square over 2G is equals to P1 minus P2 over rho G. Okay, can. So there's two velocities here, C1 and C2. Okay, but we are not interested in two velocity. We just need one of them. So we can do some substitution. So the substitution we use is A1 C1 is equals to A2 C2. Okay, can. Wait, let me just try to follow whatever that's in the slide. Okay, so in terms of C1, okay. Okay, so I want everything in terms of C1, so I will replace my C2. So C2 is equals to A1 over A2 C1. Okay, so this is my equation 1, and this is my equation 2. So I will substitute equation 2 into equation 1. Substitute 2 into 1. All right. So this one will become A1, A2 square C1 square minus C1 square over 2G is equals to P1 minus P2 over rho G. Okay. So I will take out my C1. So C1, I factorize out. So if I factorize out my C1, inside will be A1 over A2 square minus 1 over 2G is equals to P1 minus P2 over rho G. So remember what I say? I want C1 as my subject. So C1, okay, the 2G I'll bring it across, P1 minus P2, cross multiply, over rho G times A1 over A2 square minus 1. Okay, and not forgetting my square root. So this will be my C1 expression. All right, based on Bernoulli's equation. Okay, so of course, if I want the flow rate is what? Flow rate will be AC1, A1C1. All right, so I just add an A1 in front. So this will be my flow rate. So the flow rate can be calculated by this formula, but provided that we know our pressure difference, P1 minus P2. Okay, so we'll measure P1 minus P2. Then I'll sub into this equation, and this will give me my V dot. Okay, can. So this is the derivation for the formula for Venturi meter. Any questions so far? Okay, I have a question. Yes.
I don't get it. The part where which line? 1, 2, 3. Just below the sub 2 into 1, whereby the A1 over A2 square, C1 square. That part I don't get it.
Okay.
Like,
so
why did you
understand.
like square the thing?
So you see, number 2 is this one, right? A1 over A2 C1. correct? So I'll replace this expression into this C2, correct?
Okay. Yeah.
So I can do it here. If it is C2 square, this is equivalent to everything square. A1 over A2, C1 square.
Ah.
Then based on your indices, you can separate the power to A1, A2 square, C1 square.
Okay, noted.
Okay? Yeah, so this is why we get this. No problem. It's good to have questions. Okay, so because seldom during live session I have questions. It's always a one-way talk. Okay, so this is our flow rate derivation. So that is what you will see in your notes. Okay, let me bring back the notes. Okay, so this is the same equation that you see here. So at least now you know how to derive it. But remember, for our module, derivation is not a must. Derivation is only for understanding. I'm deriving here today so to improve your understanding, but it will not be tested directly. Okay, but of course, it will be good if you can derive by yourself. Okay, especially for those who are who will be pursuing a tertiary education in the university, then derivation becomes even more important. Okay, so yes, here we have it. This is the Venturi equation, but you realize that this Venturi equation has something different. Okay, it has this CD term. Okay, but just now when we derive the whole thing, there's only this part. Okay, so this part here, okay, is actually what we call the V dot theoretical, because it was theoretically derived. Okay, when we say we theoretically derive it, it means that we assume that there's no losses, there's no friction, there's no other forms of losses. So to account for these losses, okay, if we want to find out the actual flow rate, then it is a practice to multiply some sort of coefficient to the theoretical value. So this coefficient, we call it CD, coefficient of discharge. Okay, and this discharge value, okay, will have to be determined experimentally. Okay, so the value will differ every time. Okay, so for this Venturi meter, we will be doing a lab on this, based on this. Okay, so same thing, later on, I'll tell you when to go to Mel. Okay, you will see a video of me doing the experiment with a Venturi meter. Okay, then you will have a better understanding of what we are actually trying to achieve here. Okay, so but the bottom line here is that the actual value, okay, will be a multiple of a CD times the theoretical value. Okay. Okay, so it's that simple. It's only one equation only. Okay, so we can look at the example. Okay, so we have a horizontal Venturi meter filled to a pipeline of diameter 0.5 meter, carrying a oil of specific gravity 0.83. Okay, so the mercury with a specific gravity of 13.6 has a manometer connected between the throat and the diameter 0.2 and the upstream, giving a difference in the mercury column of 30 mm. Okay, so point number 2 here, okay, we call it the throat. Okay, so if you're wondering what this throat is, this throat is referring to point number 2. Okay, so we are asked to calculate the difference of the pressure, then the velocity at 1, and the flow rate. So how do we calculate the difference in pressure? Okay, so this one is based on what you learned in chapter 3. Also later we will use this as a chance to recap. How do we find out the pressure difference between this manometer? So the manometer displayed a 30 nm height difference. Okay, so how do we convert that into pressure? So based on what we learned in chapter 3, okay, pressure along the same height must be the same. Okay, so the pressure at point 3 and point 4 must be the same. So we start off with P3 equals to P4. Okay, can P3 equals to P4. So if you look at the diagram, or what I'm saying here is pressure at the same height is the same. So these two are at the same height of the same fluid. So P3 must be equals to P4. Okay, so the equation for this pressure works based on this theory. Pressure of the same height of the same fluid must be the same. So P3 equals to P4. Okay, so P3 equals to P4. So what is P3? P3 is everything that is above it. All right, so what is above P3? Let's look at the diagram again. So above P3, okay, will be 30 mm of this, X of this, and P1. So if I were to write P3, P3 will be equals to P 30 mm, okay, the 30 mm column of water, plus P X mm of water, plus P1. So that is my P3. Or the pressure at 3 is due to everything that is above it. Okay, same thing for P4. So how do I write P4? P4 is everything above it. So for P4, we have 30 mm also. So but today the 30 mm here is the 30 mm of mercury. Okay, so the fluid is different. Inside here, this 30 mm is mercury. Plus px mm of water. Okay, this x is the same because it's water. Plus my P2. Okay, so this is how we write out P3 and P4. Okay, P3 and P4. All right. So any questions till now? Okay. Okay. So once you understand the derivation, so you understand why this thing is being written this way. Okay. So the left hand side is P3. Okay. The right hand side is P4. Oh, just now I made a mistake. The fluid we are using here is oil. Okay. So it's not water. So it should be P 30 mm of oil and PX of oil. So just a small correction. It should be oil, not water. All right. So since PX is the same, so PX can be cancelled on both sides because both PX are PX oil. All right. So we rearrange, we bring the P1 and the P2 to one side. Because remember what we want to do is to find out P1 minus P2. Okay. So this term will go to the other side. Plug in the values and we can calculate. Take note, the density of mercury is the specific gravity times 1000. So 13.6 times 1000. Density of oil is the specific gravity of oil times 1000. Okay, so you'll get this value here. P1 minus P2 from the manometer is 3758.2 Pascal. Okay, so once we have the pressure difference, as I told you just now, we just have to sub inside our formula here. P1 minus P2. Okay, so P1 minus P2, sub in. The rest also can sub in. Another thing to take note here is your area, cross-sectional area. So cross-sectional area, the formula is pi over 4 d square. Okay, so for A1, the diameter is 0.5. For A2, the diameter is 0.2. So please sub in accordingly. Okay, then you will get your flow speed. From your flow speed, to get the flow rate, okay, use your A1C1. That's it. Okay, can. So it's relatively easy. So long as you understand the working principle, all right, and even better if you understand the derivation that I did just now, you realize that this chapter 5 is really nothing. End of the day, is just plugging in the values only. Okay, most importantly is you need to find out your P1 minus P2. And P1 minus P2 is based on the concept from chapter 3. Okay, so any questions up till now? Okay, no questions, then I'll move on. Okay, let's look at another example. Okay, so we have a Venturi meter connected in a vertical pipe, okay, which carries the water. Okay, the diameter of the entrance and the throat is 150 and 75. A mercury U-tube manometer is connected to the entrance and the throat. The height difference between the throat and the entrance is 150. And the actual flow rate is 40 liters per second. And the coefficient of discharge is 0.96. Calculate the pressure difference between the entrance and the throat. Okay, so 5.2 is the other way around. Okay, it's different from 5.1. 5.1, they want you to calculate the flow rate. Okay, so I write here, for 5.1, I want you to see the difference. 5.1, okay, they give you the pressure and they ask you to find out the, oops, sorry. Okay. They give you the pressure, they ask you to find the flow rate. For 5.2, it's the other way around. They give you the flow rate and they want you to work backwards and find out the pressure. Okay, so see the difference between these two examples. Okay, so today we are given that the flow rate is 40 liters per second. Okay, so we are asked to find out the pressure difference. Okay, so basically we have to reverse everything. All right, so how do we do it? Wait, something hang. Oops. Give me a minute. I think my... Okay, so we have to do it the other way around. Okay, to find out the pressure difference. Okay, one important thing to take note also over here is that you realize this is a vertical Venturi meter. Just now, whatever that we derive, this formula is for horizontal Venturi meter. Okay, I say again, this is for horizontal only. What's the main thing? For horizontal, Z1 is equal to Z2. So we cancel off these two terms. Okay, when we apply the Bernoulli equation, correct? That's what we cancelled when we did it just now. Oh, Z1 and Z2 was cancelled. Z1 is here, cancelled, Z2 is cancelled. So meaning to say that this equation cannot be applied for 5.2 because 5.2 is vertical. All right, and it is very clear to see that if you use Z2 minus Z1, it's going to be 150 mm. Correct or not? That is basically the height difference here, 150 mm. So meaning to say that for this question, we cannot use whatever that we derived just now. All right, we need to start from scratch again. All right, so how do we do it? Okay, so of course, before we start deriving, okay, we can find out our C1 and C2 first because we know our flow rate. Okay, so we can work out our C1 and our C2. Okay, basically for 5.2, we are doing it the opposite way of 5.1. 5.1 is we calculate C, then we calculate flow rate. But 5.2 is we use the flow rate, we reverse engineer and find out the C first. Okay, so find out your C first. Okay, using V dot equals to AC. So for the C1 is V dot 40 liter per second. Please divide by 1000. Okay, to change it to meter cube. The diameter is 150 mm. So divide by 1000 also. For C2, the diameter is 75. Okay, can. So we get our C1 and C2. So next, we apply our Bernoulli equation. So as I mentioned, we need to re-derive it again. So this time round, we cannot omit the Z1 and Z2. Z1 and Z2 must be there. Okay, can. So what we want to find out is the pressure difference. So again, we group the pressure on one side, P1 minus P2. Okay, can. I think there's an alignment error. This one is one equation. Okay, then this one is the second step. So this is step 1, this is step 2. So step 2, I group my P1 minus P2 on one side. Then I cross multiply and bring the rho g to the other side. So the rho g appears here. Okay, can. So it's good if you can take a pen and paper and try to write all this down yourself one more time. Then you can get a feeling of how this whole thing works. Okay, but essentially it's still the same equation. It's still Bernoulli. We are not going anywhere else. All right. It's just a matter of shifting the variables around. So once you take a pen and paper, you do it, you'll be very clear. Okay, but again, remember it all boils down to self-discipline. If you want to do it, you will do it. If you don't want to do it, nobody can force you to do it. Okay, and if you don't do it, the conclusion is very simple. You might not be able to understand it. Okay, so once you have this form, P1 minus P2 equals to rho g, you can just plug in the values. So rho is 1000, g is 9.81. Okay, C2 and C1 is what you calculated. And as I mentioned just now, the height difference is 150. Okay, so you can work out your pressure drop, 79896. Okay, clear? Okay, next. So with the pressure difference, find out the height of the mercury. So again, see, work backwards. Now we want to find out the height. 5.1, we are given the height difference. So now we have to revert back. So same thing, we will take this as P3 and we will take this as P4. So same concept. All right. So P3 must be equals to, so let me write here, P3 must be equals to P4. Same fluid at the same height must be the same. So what is my P3? P3 is everything that is on top of it. So we have this part, and this part. So there are 3 parts to it. Okay, so P3 here is equals to, we have pH, okay, which is this part. This is pH. pH water. Okay, this time is water. Correct. Then next part is here, the small one, which is X. So plus px, also water. Okay, then plus P1. Okay, so some of you might be wondering, how come Mr. Lau is drawing this arrow here? Okay, so P1, remember, fluid at the same height has the same pressure. So if this point here is P1, here must also be P1. So this is P1, this must also be P1. So everything on top of P3 is P1 plus Px plus pH. Okay, likewise, P4 has what? P4 has pH, but pH is mercury. Or pH is mercury, this part mercury. Next, also Px. Px is water. And we have one more portion here. And what is this portion? P150 and also water. Okay, how do I know this is 150? Because from here to here is 150. And lastly, as I mentioned, if this is P2, this must also be P2. So plus P2. So P4 has 4 terms. Okay, so once we have my P3 and P4, I can equate them. Okay, so let's look at the solution. Okay, so if you have understood, all right, P3, as I mentioned, okay, will be all this. And P4 will be all this. Okay, so same thing, my PX cancel. All right. I will want to, because I want to find out my H. H is my unknown. So I group all my H terms on the left. So where are my H terms? H term is this one, consists of H, and this one consists of H. Okay, so rho M GH minus rho W GH. P1 minus P2 are grouped together. All right, and this one is the 150. Plug in the values. Density of mercury, G. Density of water, G. P1 minus P2 that we calculated in part A. All right, density of water 1000 and my height 0.15. So from here, we can get our final answer of H, which is 0.311 meters. Okay, Ken, clear? So this is for 5.2. Any questions so far? Okay, okay, so let's move on. Okay, so I will try to cover up to Orifice today lah. Okay, we'll leave the last one to next week, because anyway we got 2 weeks for one chapter. Okay, so for Orifice, the concept is the same. If you remember hearing me say, the principle is the same. So the principle is I must create a constriction. So this here is my constriction. Can you see? But of course, instead of a gradual constriction like your Venturi meter, Venturi meter is a gradual one. Today, what we put here is my Orifice blade or plate. Okay, basically it's a plate lah. This pink color thing that you see here is a plate. Okay, so this plate here has a very sharp edge, and it also reduces the flow. Okay, so since the principle is the same, so for a horizontal orifice, horizontal one, horizontal means what? Z1 equals to Z2, which is equals to 0. You see, the formula is exactly the same. All right, so I don't need to derive it anymore because it's the same formula for horizontal one. Okay, everything is exactly the same. So same thing, we need to find out P1 minus P2. The P1 minus P2 will be given by this height difference here from the manometer. All right, so once you have P1 minus P2, I can plug into the formula. And same thing, CD, all right, is again the coefficient of discharge. Okay, to account for the losses. Okay, so since everything is the same, we can straight away go into one example. All right, so we have an orifice, okay, fixed to 100 mm pipe carrying water. So the orifice diameter is 25 mm. So the orifice diameter here is referring to this gap here. Can you see or not? This gap. This gap here. Okay, this gap here has a diameter of 25 mm. Okay, usually the orifice plate, okay, if you look at the cross section, it's just a hole in the middle. Okay, this is the cross section. This is the side view, sorry. This is the side view. But if you look at the cross section, it's going to be looking like this. Okay, it's just a hole in the middle. So the hole here is 25 mm. So a YouTube manometer is connected All right, and the height difference is 135 mm. Okay, so to calibrate the orifice, 550 kg of water is collected over an interval of 5 minutes. Calculate the coefficient of discharge. So what the question wants here today is to find out my CD. So how do I find out my CD? To find out my CD is based on this formula. V actual equals to CD V theoretical. So if I want to find my CD, I need to find out my V actual and my V theoretical. So V theoretical is based on the formula that we have seen just now, that we have derived just now. How do we get the V actual? What is V actual? V actual is from the experiment. So from the experiment, 550 kg of water is collected over 5 minutes. Okay, so V actual, you can actually calculate by a simple formula, volume divided by time. Okay, so for the volume wise, okay, since I'm given 550 kg, so I must use mass divided by density, divided by time. So mass is 550, density is 1000. Oh, sorry. And the time is 5 minutes. Change to seconds. Okay, so you should be able to interpret this from the question. All right, how do we get V actual? It's just volume divided by time. Okay, so let's go to the solution. Okay, the solution will show the same thing. Okay, so over here, you see, this is the V actual that we did just now. Okay, can. Okay, so how do we, so same thing, I need to find out my P1 minus P2. So P1 minus P2, okay, I must use my chapter 3 concept. P3 is equals to P4. Okay, so maybe we will go back and let me show you again. Okay, so P3 and 4. Okay, so P3 is everything above it. What is above P3? This one, which is P135 water plus this portion here, okay, which is Px, because we don't know, but it's not important because later you will cancel out. We say this is X, the total height, plus my P1. How about P4? P4 is same thing, P135, but today this 135 is mercury, plus my Px, water, okay, this part, plus my P2. Okay, so it's the same step, P3 and P4. All right. So once we have that, okay, I can equate P3 to P4. So as I mentioned, your Px can cancel off. All right. So rearrange, group your P1 minus P2 on the left because that is what you want to find. Okay, can. So plug in the densities of mercury, water, and you can calculate my P1 minus P2. So once we have this, I can apply the orifice equation, which is the same as the Venturi one. So P1 minus P2 will come here. Okay. So based on this equation, V actual, okay, take note, is what we calculated using the actual flow rate, the 550. CD is my unknown. Okay, the rest you can plug in yourself. Okay, the area and cross-section area. All right, so then you divide across and you can get your CD value. Okay, remember, the best way to learn this is take a pen and paper, write everything down one time yourself. Then you will see. Just by observing me doing it, doesn't matter whether is it online or on the whiteboard. Doesn't matter whether am I live or not live. Okay, today I'm live. So But again, I don't see a difference. Okay, most importantly is you must follow, take a pen, take a paper, try the calculation here yourself. Then you realize that it's actually not that difficult. Okay, Ken? So that is how you calculate your CD value. Okay, so I will stop here today, all right, for this chapter 5. Okay, so I'm only going to cover this first part for chapter 5. Next week, all right, next week I will move on to the second part, which is the part on pitot-static tube. But bear in mind also, okay, the principle of the pitot-static tube is also almost similar to what we have learned today. All right, so but just to manage the content a bit, I've decided to stop here. All right, so next week we will